This is the conversation with Matt Strassler. He's a theoretical physicist, formerly a professor of physics at University of Pennsylvania, University of Washington, and Rutgers University. He's a long-term member of the Institute of Advanced Studies and an associate at the physics department at Harvard University. He's also the author of the book Waves in an Impossible Sea. In this conversation, we discuss his love for physics. We talk about foundational concepts like particles, waves, wavicles, fields, energy, mass, and then we talk about the Higgs field. This is no time. If you like what you see, then do hit subscribe on YouTube, follow on Spotify, rate 5 stars on Apple Podcasts. This project takes a lot of my time, money, and efforts. If you'd like to see it continue, do consider making a donation on Patreon, Anchor. You can buy a gift on Instagram. You can join as a member on YouTube. You can buy super thanks on YouTube. If not through monetary channels, then do consider sharing these episodes, leaving your likes and comments. All forms of engagement, they really go a long way. For the forms of love and support, you can follow this channel on Instagram or Twitter, or follow me personally. And now, it's no time. When you were 10 years old, you sat on a flight to Florida with your family. Mm-hmm. You sat on the left side in an eastward-facing window seat. Midway through the flight, the pilot announced that the flight's going to be diverted from its route because a rocket's going to be launched from Cape Canaveral. You wrote about that experience on your blog in the following words: "What I saw through the window made me gasp. In the distance, a little silver needle was riding an ever-growing white thread. It climbed to our altitude and then rose above us, higher and higher. And as I watched, marveling, I suddenly grasped for the first time the true meaning of space. Before that moment, it had been a fascinating abstraction. Now, I was watching a rocket actually go there. There. It was a real place and not very far away." So for my first question, I want to go back to your childhood, to 10-year-old Matt, or maybe even further back. When you look back now in hindsight, are you able to pinpoint how, when, and where you started falling in love with physics, with space, with the universe, with the nature of reality? Do you know what it was that attracted you to physics in the first place?
Well, I think there were several things, and they do go back very far.
Okay.
And so it's hard for me to really know. I was already interested in reading about space when I was 4. I remember a book about the planets that I devoured at that age. And I think part of it was that I spent some of my time here in New York City, where I was born, but I also spent part of my time in Western Massachusetts, where I currently live, out in the country. And so the experience of being able to go out at night and see the stars in a really dark setting, not like, suburbs, but in a place where you can really see the thousands of stars that are visible to the naked eye, that was a very special experience for me. I was fascinated by it. But then, of course, here in New York, you don't see that, but you have the planetarium. And so there's this, urban, rural part of me that also experienced, at a very young age, experienced the universe both very visually, but also experientially at sort of intellectually at the planetarium, where you get to sort of learn what it is that you're actually looking at. And so somehow those two things together, I think, were very important to me. And the fact that we are also family friends with a well-known astrophysicist didn't hurt either, because even though and we didn't see them very often, but when we did see them, this fellow would show my dad pictures of what he was working on. And I had no idea what they were talking about, but boy, those were cool pictures. And I was always of the sort who wanted to know, what am I looking at? What is happening? And I think the experience that you just described of the rocket and the transition from knowing that, oh yeah, space is this place out there, and there's these things that move around in it, and there's people who go there, and it's all sort of a story, to having a visual, almost tactile experience that says, oh, wow, there it goes. And it's going to be there in 5 minutes. That's all it takes for a rocket to get into, above the Earth's atmosphere. That it's a little bit like having a part of the world which is vague and, has a "There Be Dragons" sign drawn on it on the map. Suddenly it comes into view and becomes clear. Oh, it's that far away, and suddenly I'm thinking to myself, well, I guess it's going to be 200 miles up. Gee, it's about 200 miles from New York to, I don't know. I think it's 100. Boston's a little closer than that. But, that's the only distance we're talking about. The Earth's atmosphere is this very thin shell. And so for me, I think the experience of being a physicist has been that of getting away from the there be dragons part of the universe and coming to grips with it more and more over the years. And I started very young with that.
As you came to grips with it, do you know what mysteries really captivated you? What were the big questions that really excited you at that age?
Well, certainly when I was very young, I was fascinated by the planets and fascinated by the distances, which are so huge, and the sizes, which on the one hand are huge, and on the other hand tiny, in the sense that, planets are much larger than we are, and some of the, Jupiter's a lot larger than the Earth, and the Sun even larger than that. But of course, the distances between them are even greater. And so, I was one of those kids who did sort of try to lay out the planets in little, the Jupiter was an orange and Earth was a grape or whatever it was, and I laid them out on the hallway, and of course, you can't do that because the distances are so vast that if you try to make the planets into macroscopic spheres that you can see, then the distances go for hundreds of feet. So the inability to grasp the sizes and the distances that are present in the solar system, I think, was something I confronted at this early age. I couldn't have been more than 6 or 7 when I did that. And it made me, it fascinated me, and it made me struggle early with these questions of how do I visualize these things? How do I understand these crazy things that the world has to offer us? And so I think that was very important at that very early age. And then, black holes and the curvature of space. I mean, that's another thing which one struggles with when one first learns about it. How the heck do you think about that? And I guess in some ways I still do struggle with that, although I know the techniques for doing so now. And then the most stunning of all is when you, as a youngster interested in science, learn about quantum physics, because it makes no sense to the human brain. We as individuals and as a community have struggled to find ways to think about it that would satisfy us as human beings, and we still don't really have them. And while the more I learned about the way the universe works, the more I wanted to try to understand it as best I could. So those stages, I think, of basic astronomy, learning about curved space and relativity, and then learning about quantum physics, each one of those was another milestone along the path of dragging me in so that I could never get away.
Such important ideas, such powerful ideas. Do you remember what book it was, that book about planets, when you read at the age of 4? Do you still have that copy?
I don't, I think, because of course it was a book that a 4-year-old, well, at least a 6-year-old could read. And I have a visual in my head, but I don't know what book it was. I don't remember. Yeah, I read so many books. I love to read.
Yeah.
And I read constantly, but there's very few books about science that I remember really strongly, because I think I just devoured a lot of them and they built up over time. And now, having written one and recognize how, on the one hand, how challenging it is to do it well, and remembering how often I was frustrated by the books that I read, I think that the really, really good books about science, especially about the more abstract sciences such as physics, are few and far between. And that's certainly something we can talk about. Why is it so hard to write a book about these subjects?
Let's talk about it. I definitely want to pick your brains on this. You're an excellent science communicator. Often in your book and in your blog as well, you're focused on trying to make these ideas accessible to a lot of people. So maybe this is inspired by that book of planets that you read that was so accessible to you as well. You try to not use a lot of math and formulas so you don't scare the people away. You try to use a lot of analogies so that dumb people like me can understand really complicated ideas. Albert Einstein, and this name might ring a bell, he had once said that everything should be made as simple as possible, but not any simpler. You just spoke about the challenges of writing about science. How hard is it to dance that dance? How tough is it to balance explaining an idea just as it is? If it's complicated, so be it. It has to be complicated, and put in the onus on the listener or the reader to put in all the work and come up to that level so they can really grasp the depth of the idea or the power of the idea, as compared to trying to simplify the idea or dumb it down, to use a very common phrase, even if that means you're painting a picture that's too simplified or maybe quite far away from reality. Is this something that you find challenging?
Well, I think the key challenge, if I can say it slightly differently, is that both of those extremes that you just mentioned, where you dumb the idea down, losing its essence, or you explain the idea with so much detail that it becomes impossible for a person without mathematical background or a lot of experience to understand it. I think those two things are to be avoided. And what lies between is not exactly a compromise between those two things, but let's say an ideal third way,
okay,
which is to find a way of thinking about the complex idea in a simpler fashion, so that it isn't so hard to explain after all, if you just do it in the right way. And it happens that as a scientist myself, I have always needed to do that. So some of my friends are really fantastic mathematicians, and they can handle extraordinarily complex ideas in their heads, and I'm always amazed by what they can do. And I'm not that kind of guy. I have to find a way to make it simple enough that I recognize how this idea relates to other ideas that I already know.
Yeah.
And it's almost always true that there is a way to do that. And so I think maybe years of experience doing that for myself has given me confidence that if I think about the idea long enough, I will find a way to explain it that, avoids either of those two extremes and finds a path where it is certainly not, the intention is not to write it so that, it can be, it's not, I wouldn't want to say that I'm writing for people who can't understand these things. I'm writing in a way for people who, I'm trying to create a path by which a person can understand these things much more quickly. And I don't really believe that a lot of these ideas are too complicated for the average person. They're not. It's just the explainers haven't come up with the right way of explaining it yet. And there's a long history of things that were once thought too complicated for the average person, which are now taught in grade schools. And that's something we should recognize, that historically we have found better ways of doing things over time. And so my feeling is that, I just want to be a part of that process of taking things that are considered to be too hard and making them as accessible as I think they should be.
I love it. Let's channel that energy for the rest of this conversation. This is pretty much what the premise of the show was built on, that I used to find so many topics used to feel unwelcoming, but it's just a matter of how you approach it and how you explain it. So let's do it. Let's assume I'm a 5-year-old who's trying to understand particle physics. I know it's not much of a stretch. Easy to imagine. Mentally, I'm already there. Let's assume I'm a 5-year-old who wants to understand the structure of matter. So let's take an ordinary object. Let's take this Lego block. If I try to break this down further and further into molecules and atoms and even smaller pieces, as I keep breaking this block down, what do I see?
Well, you've half answered the question already, right? I mean, it's certainly true. As you break it down, you will discover that the fundamental ingredients of matter are atoms. And by matter, we should already take a moment. By matter, what do we mean? We mean ordinary stuff.
Right.
When we start using the word matter in other contexts, it might get confusing because people use it in different ways. But at least for ordinary things around us, they are all made from atoms. And the only thing we encounter that's not made from atoms is light. So our ordinary world is basically shaped by those two things, atoms and light. And we could leave it at that and just talk about how atoms interact with each other and do all of chemistry and biology and many other things, and we would be fine. And we wouldn't have to go any further. And so for a 5-year-old, I probably would stop there.
Okay.
Unless it was a particularly insistent 5-year-old, such as myself.
Yeah.
And in that case, I would talk about the fact that atoms too have a structure. They're not the fundamental ingredients of the world. They're not the bricks out of which everything is made. And on the outside of atoms are particles, and I would use the word particles for a 5-year-old, called electrons. And in the center of an atom, very, very small center, is something called the atomic nucleus, which in turn is made from particles called protons and neutrons. And again, I would probably stop there for the 7-year-old. But the particularly insistent 5-year-old or 7-year-old would then get a tour of a proton or a neutron, which is a very complicated place. And I would tell them that, well, just as there are electrons on the outside of an atom, and those are believed to be elementary particles, basic building blocks of the universe, inside protons and neutrons, one finds particles called quarks and particles called gluons, which are also believed to be elementary ingredients of the universe. And I would probably leave it at that. I would leave out all sorts of subtleties, which, of course, for a 15-year-old, I might consider adding. But, the basic idea that the elementary particles out of which we and all ordinary matter are made are atoms which are organized as electrons on the outside and particles made of quarks and gluons on the inside. That's the basic structure of ordinary matter. There's a lot more in the universe. And part of the story of 20th century physics was discovering that there's a lot more. Quarks and gluons themselves weren't even understood and discovered until the 1970s, so they're a fairly recent addition. And electrons were only discovered in some sense in the 1890s, so this is pretty recent history. Humans have not known these things for very long, and there are still many elements about them that we are in the process of getting straight.
I'm an insistent 5-year-old, and you have constantly used the word particle. So I'm going to ask you a potentially silly question. I'm a 5-year-old. I can take these liberties. What is a particle?
Not a silly question at all, as you are well aware. The problem with explaining physics, this is a key issue in writing a book about the subject, is that the first thing that gets in your way is language. And this is not only true for physicists trying to communicate with non-scientists, but it's a problem for physicists communicating with each other and even with themselves. And we are often subject, even as professionals, to not exactly misleading ourselves in a way that would affect the way we do physics, but misleading ourselves in a way that we think about the physics by the words that we use. And sometimes those words really get in the way. And the word particle is a particularly problematic one because, like many words that we use in physics, it is a word that comes from an existing language, in this case English for us, and it also exists in many other languages that use it, particule in French, for example. And the problem is that word comes with a lot of baggage. And what is that baggage? Well, when you think about a particle, normally you think about, let's say, a grain of sand or a particle of dust floating in the air. That's the concept.
Mm-hmm.
And so it's a little localized thing, like a tiny little ball. And so elementary particle, you now think in your head, you picture a tiny little ball, smaller than you can imagine, but it's a little ball. Yeah. Or maybe you even imagine it going down to infinitely small size where it becomes a point. And physicists will talk about a point particle, meaning something like that. The problem is that there's a lot of things that electrons do which this image of particle does not capture. And some of those things are absolutely critical. So, for example, if I took a box and I put a particle in it, what's it going to do? Well, I don't know. The particle will go somewhere. Probably if there's gravity, it'll go to the bottom of the box. If there's no gravity, it'll just float around in the box somewhere. And that's it. And there's not much to say. But if I put an electron in a box, it in a sense fills the whole box. And it vibrates while it's there, which is a very different thing. So why are we calling an electron a particle if it does things like, expand to fill an entire box that it's placed in and it's there vibrating? It's somehow the wrong starting point. So you can ask yourself, well, how did it happen that electrons were called particles in the first place? Well, it's because the first manifestation of electrons that was discovered was something called a cathode ray. It's a beam of electrons we know today, but they didn't know. They just had some thing that traveled in a straight line and made a spot on a screen. And okay, so and you could make that spot small, so these things weren't spread out across the entire apparatus. So there's this narrow beam of stuff, you don't know what it is, and eventually people realize that that beam is made from lots and lots of objects which are all the same. They all have the same mass and electric charge, and we'll give them a name. We'll call them electrons. And so if you see a bunch of objects that travel in a beam, what's your natural thought? Well, if I have a bunch of things traveling in a beam, it's probably a bunch of particles going in a straight line. Reasonable thought. Now, on the other hand, we've all played with laser pointers, and laser pointers are narrow beams of light, but those are waves of light. So it's not instantly obvious just because you have something traveling in a beam that it's little dots traveling in a beam.
Yep.
And on the other hand, when in the 19th century, one would have said that light is just a continuous wave, so you wouldn't have talked about particles in that context. So the notion very early on was that, okay, there's these electrons which travel, which are particle-like and travel in straight lines. And then you have electromagnetic waves, which are light, which had already been discovered and understood in the middle of the 19th century. And then in 1905, Einstein came along and said, yeah, but you can't explain this thing called the photoelectric effect unless light comes in packets. Quanta, as he called them. And so this is the birth of the quantum idea. And this is where waves and particles start to come into contact and into conflict as ideas. Previously it was easy. Atoms were particles. Maybe they were made of smaller things, but in any case, they were particle-like. Electrons were particles. Light was a wave. And now Einstein says, yeah, but something about light is particle-like. Now, this was a proposal that would explain an experiment. And a lot of people didn't believe him for good reason, because light shows interference. If you pass light through two slits or through a diffraction grating, you'll see all sorts of crazy interference patterns. And we're used to the idea that all waves show interference. Water waves show interference as well.
Yeah.
So people already knew from the 19th century that light was a wave. And so here, what Einstein was telling them that, this young kid, let's remember, he was in his 20s, is proposing that light is made somehow of packets. It makes no sense. You're not going to have an interference pattern. But he was right. And we are still grappling with the fact that he was right, that somehow light can exhibit both interference and particle-like behavior, which does not mean, you notice I was careful to say particle-like. It does not mean light is made of little dots. But it is true that light is made from something called photons, which physicists tend to call particles. But they're only particle-like in certain senses. And they have this other strange feature that, like electrons, you put photons in a box, they will fill the box, and they will vibrate. In fact, that's how lasers basically work. And so, you have a little ruby crystal, and the light is in there vibrating and forming a standing wave inside the ruby. So this conflict that goes back to the beginning of the 20th century between the words we use and the concepts we use and the behaviors of these objects has caused significant confusion in physics classrooms and in books about physics for the public. And I would dare say it even causes confusion among some professional physicists too, those who don't have to deal with the concepts on a sort of regular basis. But for those of us who work in particle physics on the theoretical side, who have to become experts in quantum field theory. Quantum field theory is very clear about this. It is not true that electrons are particles of one type and photons are some other thing. Photons and electrons are treated on the same footing. And so whatever is true about photons, whatever wave-like properties photons have, and whatever particle-like properties electrons have, well, they both have them. And the difference between them is one we can talk about in a little bit, but the fundamentals of quantum field theory treat them on the same footing.
I agree. There is this conflict and there's already a disconnect because I grew up learning it this way. I'm sure others do as well, that particles are these small, spherical, point-like substances that are fundamental. And from the way you've described it, it's not really particles that we have to think of. You have to think of maybe the waves that as fundamental entities. Particles happen to be these point-like approximations or these quanta of the waves itself. It's impossible to talk about particles without bringing in waves. You already alluded to it. So let's formally define it. What are waves?
Well, that too is a word which is used in English in multiple ways. Yep. And we have to be very careful about that word. And it's hard to explain well because without examples. And the reason is that waves can do a lot of things. So let's first say what we're not talking about. You go to the beach and you surf a wave. Each wave is a piling up of the water, a crest of the water. There's a trough in front, there's a trough behind. That's what your surfer will call a wave, and most of us at the beach will call a wave. That is not the type of wave that we're referring to here. Mm-hmm. We're talking about waves in the way that a recording engineer might talk about a wave. For example, as I'm speaking, am creating a sound wave, which this is not a single piling up of the air, but a whole sequence of crests and troughs. So it's a wave that in the sense that it looks like this. It's not just a single bump in the water. It's the whole wave train, as we might say in English. That is what particle physicists mean by saying that a photon is a wave, or that light is a wave. We're not saying that light is a single crest. And so this is important because what you don't want to think of in your head is that you replace a little dot. You say instead of electron being a dot, it's this single crest. No, that's not it either. In general, an electron can do many things. It can have all sorts of complicated shapes, just like water waves, or wave in the singular, as a physicist would say, can have many shapes, just as a sound wave, the sound wave that I'm making right now, is very complicated. So the wave-like behavior of electrons it's not possible to draw it with a single picture, because waves can do all sorts of things. So if you want to really capture all the things that are wave-like about an electron, you'd really want to think about it in a lot of different settings and focus on the fact that, it can be this shape in this context. It can be that shape in that context. It has all this flexibility that waves have, and particles don't. So that's very important for light. If light had a fixed shape, we couldn't do all sorts of crazy things with it, and it wouldn't do all the wonderful things that it does in life. Same with sound. Mm-hmm. So in a sense, the wave-like properties of electrons and photons are used by nature it creates a flexibility for nature that allows for all sorts of wonderful structures. And in a sense, part of the wonderful thing about atoms is that they create a setting in which electrons can do all sorts of fantastic things, leading to the great variety of chemical and magnetic behaviors of ordinary materials.
I'm glad we are separating the linguistic restrictions of these words that we use. There's waves, particles, theory is another one. Let's talk about another important concept, fields. So what is a field?
Let's hold off on that one a little bit more, because there's one more concept we haven't quite gotten to, which I think we'll need, which is the word wavicle.
Yeah.
So the question is, if electrons are wave-like, but they're also particle-like, how do we talk about them and how do we understand them? And that will bring us to the concept of fields in a moment. But I think it's useful to have a word for these weird objects that electrons are and that photons are. And the word wavicle was invented in the 1920s to describe them, because indeed they're kind of wave-like, but they're kind of particle-like. And the thing that makes them particle-like is not that they are dots. The reason we use the term quanta, the reason we use the term particle, is that they do have the property that they come in individual units. So you can't have 5.5 photons. You can't have 7.23 electrons. You can only have an integer number, 1, 2, 3, 4, 100, but that's it.
Yeah.
Now, the waves that we encounter in ordinary life do not seem to have this property. They seem to be continuous. You could make a wave as high or as low as you want it. In other words, you could take its shape and you could, make it bigger in this sense, or you could make it smaller, and that would seem perfectly fine. And you can imagine, I could try to speak softer and softer and softer. And in principle, just keep going softer and softer and forever. Mm-hmm. And light too. You would think I could just, take the light switch, if I had a dimmer switch, and I could just turn it down more and more and more, and just gradually make the light dimmer and dimmer and dimmer as far as I want it to go. Perfect Zeno paradox, right? Half as much, and then half as much again, half as much again. But it won't work, because in that beam of light that you're trying to dim, there are photons in it, which are waves, but nevertheless come in units. And so at some point, your beam of light is so dim that you begin to realize that it's actually made from individual packets, just like Einstein said. Individual quanta, individual little waves of light that are the photons out of which the beam of light is made. And it's very strange. They're waves, and yet they come in units. That we're not used to that. We don't experience that in life. Or rather, we do. I mean, this is how our eyes see. The chemicals in our eye absorb photons one at a time. So our eyes implicitly know that this is the way that light works. But we humans don't have the experience of it, so we don't have a word for it. And that is why I think the word wavicle is useful, because it gives the notion that this is sort of the minimal piece of a wave that you can have. It's the smallest possible wave. Again, not small in the sense of length, but small in the sense of height or amplitude, as physicists would say. And so that concept is better than the concept particle, because particle comes with all this baggage. And wavicle is just a new word. You don't know what it means. That's actually better, because it separates the concept from its history and from this picture that you have, which is misleading. So now this word was invented in the 1920s, and it disappeared. And I more and more think that the reason it disappeared was Niels Bohr. Because what happened in the 20s and 30s is that quantum mechanics received its Copenhagen interpretation, in which Bohr wanted to say that electrons are particles and waves, both. And that sometimes you have to think about them as particles, and sometimes you have to think about them as waves, and don't think too hard, because it's just, you can't understand it in some sort of complete, in some complete story, which doesn't have a gap in it. And so he wouldn't have liked the word wavicle for that particular way of thinking. And so it just didn't catch on. But some significant people have been bringing the word back. Frank Wilczek is one of them. And I sort of learned it from him, and I think it's absolutely right. It's a much better word, because it captures more of what a photon or an electron is from the perspective of quantum field theory, which is that it is wave-like. And the particleness comes in the fact that the amplitude of waves, the height of waves, is quantized, has to come in individual units. And you don't get that from the particle word.
Let's bring wavicle back into the dictionary. Okay, so we have the foundational concept in, we have got wavicles defined. Let's move to fields. What is a field?
So, one of the challenges for writing this book was that almost all of the concepts that you need to understand how modern physics works, they're one or two steps away from something that you understand. But they're always one or two steps. And the hard part is that means that a reader at each chapter or each section of the book has to make one or two steps beyond what is natural to think about. They have to take on a new concept. And then for the book to work, they have to come together.
Yeah.
It's always better when you're trying to explain something if you have fewer steps to go. And fields, we actually do know what they are, but we don't think about them the way physicists need to. So, for example, when someone asks me what is a field, one of the biggest problems is they have in their mind that a field should be a thing. It's a natural question because, I mean, it's a noun and a lot of nouns are things, right? So, if I ask you, what is a couch? Well, a couch is a thing you sit on. It's got arms. Okay. But a field is not a thing. And that's a problem because what we have to do then is talk about the things that fields are related to. So let me give you an example. Air is a thing. Okay. Air is the stuff we breathe. Air is the molecules that are in this room. It's a thing. What is air pressure? Well, pressure is not a thing. It's a noun for sure, but it's a property of the air. It tells you something about the air. It reveals what the air is doing. It will tell you that if we measured the force on the walls of this room, that's how hard the air molecules are pushing on the wall. But it's not a thing. Now, what if I told you, here's a property like pressure of a thing, but I don't know what the thing is? That's kind of abstract and hard to think about. Mm-hmm. That's kind of what we're dealing with when we talk about the fields of the universe. So let me explain that a little more thoroughly. So air pressure is an ordinary field. It is a property of air. It's not a thing. What are its characteristics? Well, air pressure can be different at different places in the room. It can vary from moment to moment. It can vary from place to place. There are equations that physicists have figured out that tell you how the pressure might change over time. So it's something concrete. It's something we can talk about. It's something we can write equations for, and it's something we can measure. That's what barometers are for. So that's one field of air. It's not the only one. Density. How much air is there in a little cube? How much? Well, the amount of air per unit volume is another field. Again, density is not a thing. It's a property of the air. The wind. How fast is the air flowing? That's another field. The humidity. How much water vapor, relatively speaking, is in a certain amount of air? Well, all of these things are fields. They're something you can measure with some sort of device. They vary from place to place and from time to time. They influence each other, which is interesting. They're not independent. And a set of scientists working in the 19th century can figure out how to write down equations for how they influence each other and how they work. But none of them is a thing. The word air or the atmosphere as a whole refers to something we would call, as physicists, we would call it a medium. That's the thing. And the fields are telling us about the thing and how it works. And in the case of air, we have all the information. We know what air is, we know what it's made of, and we can write down the pressure, the temperature, we can measure the pressure, the temperature, the density, the wind, and we can write down equations which tell us how they all work and interact with each other. Now, that's all great. When you come to particle physics, or even before it, 19th century physics of electromagnetism, people discovered that it was convenient to talk about something called fields, which you could measure and you could eventually figure out how to write equations for. You didn't really know what it was. And in retrospect, I think the best way to think about it is that it's a little bit like air pressure or air density. It's not a thing. It's probably telling us some properties of the universe. But we don't know what properties because we don't really understand what the universe is. So whereas for air, we can say, okay, pressure is telling us what air molecules are doing. In the case of the electric field, we don't know what it's telling us. And that makes the idea very abstract. It's not that the idea of a field is that strange. We know about it in the context of air pressure. It's that in the context of the universe, it's abstract because we're missing information, a lot of it. So what physicists have done over the last century or so, really 2 centuries if you count electromagnetism, is we've learned that the language of fields is a useful one. It is useful to think about the things that we are measuring in terms of some sort of
property of the universe or properties of the universe that can be measured at individual places that change from time to time and from place to place, for which equations can be written. These things influence each other. And it turns out that we can make a darn good description of what the universe does by writing down fields and equations that describe them. We can use those equations to make predictions for experiments that work. And in the end, that's the justification. The concept of fields is a good one because when we use it and we write down equations for it and make predictions using it, it matches with experiment beautifully over and over and over again. Now, what are these fields? I don't know. I don't know what the electric field is. I don't know what the electron or the quark fields are, but I know a lot about what they do. I know how to make predictions about what they will do in experiments. So that's where we are. And so it's important to understand that while physicists understand what fields do with great detail, we don't really understand what they are, with one exception. The only exception, and that is the gravitational field. And that's because of Einstein and his idea that the gravitational field, a property of something. What is it a property of? Well, Einstein said it's a property of space and time themselves. The gravitational field is telling us the curvature, the degree of warping of space and time. And that's the only example we have where there's a field, the gravitational field, and an explanation, as we have for air pressure, of what it is and what it does. Ideally, someday we'll understand what all the fields do, what all the fields are as properties of the universe or something in the universe, or maybe some other concept will arise in between. We'll think about it some completely different way. But whereas for air and its fields, we understand very well what's going on. For the universe, we understand almost nothing. There are fields out there. We don't know what they mean, with the exception of the gravitational field, which seems to be the curvature of space and time. So where does this leave us? The universe is this sort of substance-like thing, maybe. We don't really understand that. It's useful, at least, to describe it as having a shape, which is described by the gravitational field. And there are these other fields which are also present everywhere in the universe, just as the gravitational field is. Maybe they are telling us something about the universe too, but we don't know what. And that's where we are. So one shouldn't understand particle physics and its use of fields as if we understand everything. It's far from the case. We have this beautiful theory, the Standard Model of Particle Physics, which predicts everything that happens at the Large Hadron Collider and all sorts of other experiments that we do. But that does not mean that we have some sort of fundamental understanding. It also implies that we're not even sure that the concept of fields will survive long-term scrutiny. I mean, these are the useful terms now. There are always people trying to think of things in different ways. My colleague Nima Arkani Hamed would love to get rid of the concept of fields and space-time altogether, and he may well succeed someday. So any terms that we use and any approach that we use to understanding physics is always provisional. It works beautifully now. Someday we may find experiments where it doesn't work. We may find other ways of thinking about it that are better. But for now, this is the way we think about it in mainstream quantum field theory.
Constantly, you've highlighted the importance of the languages that we use and the limitations it creates. Like, it feels to me, it's possible that our usage of the word fields and waves and particles makes us reach this roadblock. And as a result, we have to now go back to the drawing board and break apart all these terms that we have defined because they're limiting in a certain way. Like, the certain limitations that come just with the idea of it. And you have to revisit this idea of fields. Maybe it's not just a property or emergent. There's some other concept you have to define. Like, we had the wave and the particle and the wavicle. Now the fields have to be revisited and maybe defined a different way.
Well, I think it's too early to speculate about this, other than just to say it's logically possible. There is no experiment which has raised any questions about the existence of fields and has forced us to think about it in a new way. There's no, so there isn't any sort of empirical reason to move away from the concept of fields at this time. The reason that my friend Nima is trying to move away from it, and he's not alone, is that there are various conceptual problems with the notion of space and time themselves. And so there are certain theoretical worries about how we are to make sense of what space and time are and how to make them consistent with quantum physics. And those, in the context of what is often called quantum gravity, since gravity is about the curvature of space and time, so if you're starting to worry about the quantum nature of space and time, you are, in some sense, doing quantum gravity. It makes you worry that space and time are going to be emergent concepts. And if fields are things that are found throughout space and time and vary from place to place and from time to time, but then you undermine the concept of space and time, well, you're clearly undermining the concept of a field also. So there may come a day, and in some sense that day has already arrived because we do have some examples. But there may come a day where we even apply those examples to the real world, in which we understand fields as well as space and time as some sort of emergent concept which arise from something more fundamental or at least different. But that's speculation. That may happen soon. It may happen decades from now. And it might, what actually happens may surprise us. So I think it's just, one should be clear about what we know. And what we know is that fields do a wonderful job of describing all the experiments that we run today. So that's a lot better than we could say for a lot of other things.
I won't hold my breath for a theory of everything. Let's define another important concept, energy. What is energy?
Can I bring us back to Wavicles first, actually?
Yeah, of course.
Because I think energy is in some sense it's an overarching concept that sits both above and below everything else. And but what we haven't done yet is draw the line between the first conversation about particles, waves, and wavicles and fields. But I think to see how the universe works, you want to draw those together. Mm-hmm. And in particular, the way physicists understand the world, particle physicists understand the world, is that on the one hand, the universe has these fields in it. And what can these fields do? Well, one of these things these fields can do is they can vibrate. They can ripple. And this is most famous in the case of the electromagnetic field, which is sort of a combination of the electric field and the magnetic field that we're familiar with in daily life. Physicists have brought them together into a single field. That detail doesn't really matter so much. But what's important is that light is a wave in this combined electric magnetic field. And now the question is, okay, what were photons again? These wavicles? And so one way to say it that's simple is that a photon is the sort of minimal ripple, the smallest, again, in height, the gentlest ripple you can make in the electric magnetic field. So if you make a laser, it's a very bright light. Mm-hmm. But if you turn it down as far as you can go, you can make one photon. Not a half, but one photon is the gentlest ripple you can make. So it's a ripple. That is a wavicle, the gentlest wave that you can make, and in this case, in this context, in a field. Mm-hmm. What's an electron? Well, in the universe, there is also an electron field, which is not to be confused with the electric field. The electron field also can have waves, and the gentlest ripple you can make in the electron field is an electron. The gentlest ripple you can make in the up quark field is an up quark, and so on. All the things we call particles of particle physics are wavicles in this sense. They are the gentlest possible ripple in some corresponding field. And for a particle physicist, that is how the world is built. You have space and time. In that space and time, you have fields. The fields can ripple
because of quantum physics, those ripples can be not arbitrarily dim. There is a gentlest possible ripple, and particles are, the wavicles are, the gentlest possible ripples in all those fields, which is why there's one type of particle for each type of field. Okay, so that's the basic picture of quantum field theory that particle physicists bring to the table. And one of the purposes of the book was to go through that idea carefully enough that by the end, a person reading the book would understand not only that this is a consistent and reasonable way to think about the world, but that it has some very interesting consequences in terms of energy and mass and frequency that we can now start coming back to, because we got to talk about energy.
Mm-hmm.
And I don't know, energy is one of those strange concepts that is hard to talk about in language, because the word, first of all, the word in English is very vague. I'm feeling like I have a lot of energy this morning.
Yeah.
Okay? That's, what does that mean? Okay. I mean, you know, we all sort of know what it means, but it's hard to put it into a precise language. And then add to that the fact that the concept in physics is very precise, but also very hard to put into words. And the reason is that energy is a thing that moves around from place to place and can be in many different forms. So that, I mean, I have to talk about lots of different things to talk about energy in any general way. But it's crucial for physicists that energy is this very general thing. And so the two forms that energy most often takes that we encounter is that it's stored somewhere. Okay, it offers the potential for something to happen. So energy stored in a battery. Okay, you're going to use that to make something happen. Energy stored in a taut bow of a bow and arrow.
Yeah,
that's what you're going to use to make the arrow go. So, or energy in a compressed spring that if you let go of it, it's going to make something happen. Right. So that's one type of energy, stored energy, which is often called potential energy by physicists, but the word potential has all sorts of meanings that can be very confusing in English, right? It's not potentially energy. It's energy with a potential to do something. So stored energy. The other type of energy is the energy of things actually happening, things moving in particular, although that's not the only type of energy of this class. But you know, if a car is moving, it has energy simply because of its motion. And so for you to stop it is going to take some effort because it's got energy, and that energy is going to keep it going. A pendulum swinging back and forth. Well, it has potential energy, it has stored energy when you let it go, and then it starts to swing. Well, the swinging, that motion, is motion energy, or kinetic energy, as physicists would call it. So there's often this back and forth between stored energy, which can be used to make something happen, and motion energy, which is the energy of something actually happening. And the amazing thing is that in ordinary circumstances, where you don't have to worry about crazy things like black holes or something, in ordinary circumstances, if you take an isolated system and you watch it behave, you release a spring or you blow up a firework or something like that, if you're very careful and account for all forms of energy, the amount of energy that you started with is exactly the same as the amount of energy that you end with. So this preservation of energy is called, confusingly, conservation of energy, which of course in English, conserving energy means something else. But in physics, conservation of energy means that what you start with is what you end up with. And there are very few properties of nature which are conserved in this sense, that they don't change. And that makes energy and the others, which include momentum and electric charge, they are very special and unique. And they play major roles in physics because they constrain what can happen in nature in a very strong way. Energy can't come from nowhere, so you can use that to prove that there will never be a perpetual motion machine that can just produce energy forever without you having to put any energy in, because that would violate the conservation of energy on line one, right from the start. So there are many things that are consequences of the conservation of energy, and and plays a significant role in physics, chemistry, biology, and basically everything.
Mm-hmm.
And it also turns out to be energy in a certain form turns out to be what we call mass, which is famous because that's what Einstein said, right? Einstein said energy is mass, or maybe he said mass is energy, or maybe he said that energy is the same thing as mass, or it's equivalent to mass, or could be turned into mass, or something. And, well, what exactly did he say? It's important to understand that because a lot of those sort of glib statements are not quite right. And when you really want to understand how the world works, you have to understand what exactly is being said. And so popular science has this tendency to take complex concepts and boil them down to a slogan. Energy is mass, mass is energy, energy is the same as mass. Whatever, however you phrase it, none of those statements are true. They're not false either. They're just missing their context, which means that sometimes they're true and sometimes they're false. So this is another thing I had to struggle with in writing the book because, people come to the table, if they've read about physics already, they have some notion that E equals mc squared means something. But it's not clear what m means, and it's not always clear what E means. So there's two problems. The first is there's different types of mass after Einstein. If you've gone through high school physics, you learned about mass, and you've learned that gravity comes from mass according to Newton, and mass is, has something to do with weight. And you learn all these things in undergraduate chemistry and physics. In high school chemistry and physics. And what you don't necessarily learn is that after Einstein came along, this got revised quite a bit. And there's different types of mass out there. And people are still arguing about what names to use. I've been gently spoken to on Twitter for having used mass in the way I did in the book by somebody who thinks we should do it in some other way. And is he wrong? I mean, look, this is a conventional choice. We as a community have to decide how we want to talk about things, but then we need labels and we need to stick with them. So I wrote the book using the following term, that there's something called rest mass that particle physicists use widely. And rest mass is a measure of how, if I have an object which is stationary relative to you and me, and I give it a push so that it starts moving, how much of a push do I need to give it to make it move in a certain way? If it has more mass, I need to give a stronger push, right? So Newton introduced this idea in his famous second law of motion, F force equals m mass times acceleration a, F equals ma. But that is still the notion of, and it's an acceptable notion of rest mass if you're not moving things too fast. Basically, what's tricky about it is that you need to make the object stationary, or at least you need to imagine what it would do if it were stationary relative to you. Newton didn't think this mattered, but Einstein realized, Einstein realized, no, you have to be careful. Rest mass is the mass of an object. It is the resistance of an object to motion when it is stationary relative to you. And that's important because there's other types of mass that increase with speed, or at least other concepts of mass. Some people would say those concepts don't make any sense, but that's a debate we don't have to have. The important thing is that when authors write about mass, particularly journalists, but also scientists, they often will say that mass increases with speed. That's not the mass we're talking about today. We're talking about rest mass. Rest mass is a mass that is intrinsic to the object. The rest mass of this object is the same no matter how fast it is moving, because when I measure it, I have to catch up with it first. So no matter how fast it's moving, I first catch up to it and then I push it. And that's very important because that, unlike many other concepts like speed itself or this other type of mass, this property, rest mass, is an intrinsic property of this object. This object has a unique rest mass that all of us agree on. And, well, intrinsic properties of objects are particularly important because they're things that we can really hang our hats on. And here's the really amazing thing. Every electron in the universe has exactly the same rest mass. No matter how it's moving, no matter where it is, no matter what it's doing, it has the same rest mass as every other. Why? Well, the first step to answering that question is that every electron is a wavicle in the electron field. Remember that? It's the gentlest possible ripple in the electron field. The electron field is everywhere. And not surprisingly, just like, water waves are the same everywhere, wavicles of the electron field are the same everywhere. Why should one wavicle be different from another? They're all the same thing. They're all the same type of thing. So that's part of the story. That is indeed the explanation for why all electrons are identical, not only in their mass, but in their electric charge and all of their properties, in fact. Mm-hmm. So it's also why all photons are identical. They're all wavicles of the electron field. It's why all up quarks are identical, and so on. So quantum field theory, because it tells you that the things we call particles are really wavicles of fields, explains why each class of particles is identical. Now, that explains why they're identical, but what is the electron's mass? Where's it coming from? E equals mc squared clearly has something to say. And what Einstein really intuited, maybe better to say that than discovered, because he didn't discover it in an experiment, right? He just sort of guessed that it must be true from a set of considerations, sort of theoretical considerations about how things must work. He intuited that mass must be a measure of the amount of energy that is secretly stored in an object. At least it was secret back then. So the mass of this little Lego is telling you how much energy is stored in it. And again, by energy stored in it, I mean, well, it's the intrinsic energy that it has. If I were to throw the Lego, well, it had more energy as it was traveling. But that's not the energy we're talking about. We're talking about the energy that it intrinsically has in it no matter what it's doing. That intrinsic energy is what goes into the equation E equals mc squared, where m is the rest mass, the mass that is also intrinsic to it. So the mass that's intrinsic to the object, its rest mass, is a measure of the energy that is internally and intrinsically within it.
Yep.
Now, Einstein guessed this, and experiments eventually bore him out, without knowing what the stuff is inside that Lego piece. He knew about atoms, but he didn't know what the atoms were made of. But what he inferred didn't depend on that. So what he was inferring was a very general relation about objects, masses, and their energy that should apply to anything. And so that allowed him, without knowing what his own body was made of, to calculate how much energy is in a human being, which terrifyingly is enough to blow up New York and all of its suburbs. It's more than a hydrogen bomb stored in a human. And if we didn't have all that energy, well, we wouldn't have enough mass to avoid being blown away in the wind, right? I mean, this energy is crucial. This is an amazing thing to say, and of course led to some terrifying developments in human society, because it turned out to be practical in certain circumstances to liberate some of that energy in weapons. And it's also possible to liberate some of that energy in power plants, but we've not figured out a way to do that with sufficient safety to be entirely reliant on it. It would be great if we could have safe nuclear power that we were all confident in, and it would just serve all of our needs, and we'd be done with that question. But it all comes back to this point that there's an enormous amount of energy stored in any macroscopic object. And without it, it wouldn't have its mass that allows it to be stable and avoid being blown away in a little breeze. So now that's objects in general. But then there's the question, how does an electron get its mass? Or what is its mass? What is it? And here it becomes really important. And this is why in the book, we cannot talk about an electron as a dot, as a little tiny particulate-like thing, and understand where its energy is. I mean, why would there be energy in a tiny dot? something should be happening, or something should be stored. Where is it stored? And when you understand that an electron in a box is not a dot sitting somewhere, but it's actually kind of filling the box and it's vibrating, now you have a chance of understanding it, because vibrating things have energy.
Yeah.
And when you work it out, it turns out that the amount of energy that a stationary electron has as it sits there and vibrates is exactly the amount you need to explain what its mass is.
Mm-hmm.
Mass, in other words, is a measure of the vibrational energy that an electron has by the very nature of its existence. Well, after all, an electron is a wavicle. A wavicle is a wave. It's vibrating like any wave. A wave can't just sit still. It has to be doing something. So since an electron is a wave, it has to be doing something. Since it's doing something, it has energy. Since every wavicle is the same, every one of these electron wavicles has the same amount of energy. How much? Well, mc squared, where m is the mass of the electron. That's how it works. It's not that complicated. It's complicated enough that it takes, a discussion. And if you really want to follow it, you should read the book, because of course I read it out more carefully. But you can fit it into a 300-page book, really 200 pages of the 300-page book, tell this story without ever using math other than E equals mc squared, and one other simpler equation, the quantum equation, which is E equals hf. That's all you need. And without ever using much, basically avoiding jargon, and without assuming that a person already knows a lot of science. So that was the goal of the book, and I think in that goal, at least, I think I achieved it. So a person should be able to come in with no knowledge of science per se, maybe just enough that they've seen that famous picture of an atom with some balls in the middle and some balls on the outside, and go from there and read through the book slowly. I mean, it's not a beach read, but you should be able to get to the end, or at least let's say to the 2/3 point, and understand why all the things I've been telling you in our conversation so far are true, or at least to the extent that we physicists know why they're true.
I really wish you were my physics teacher. Mentally, I'm a 5-year-old and I'm completely following so far. These are great explanations of wavicles, fields, energy, mass. I think to summarize this section, it's the perfect time for some poetry. This is a piece titled Einstein's Haiku, and it goes something like this: E equals FH and E equals MC squared, and from these seeds, the world. I think it's a perfect way to encapsulate everything that you explained so far. And you brought up the fact that now we can start talking about how electrons get their mass. So I think we have all the prerequisites in place to start talking about the Higgs boson. In 1964, Peter Higgs had speculated the existence of the Higgs boson. It took nearly 50 years to prove him right. And once we discovered the Higgs boson, people asked him for his reaction. And he said, it's very nice to be right sometimes. It's been a very long development over the years of the technology of building machines at higher and higher energy. And the Large Hadron Collider is the one which has been energetic enough and also intense enough in terms of the particle beams to do it. It's been a long wait, but it might have been even longer. I might not have been still around. Why were we waiting so long? Why did we invest so many resources? Why were we dying to find the God particle, the goddamn particle, as some call it? What is the Higgs boson? Why is it important?
Well, perhaps I'll start by saying that the Higgs boson is not important. The Higgs boson is a particle, or a wavicle, of something called the Higgs field. The Higgs field, that's important. Very important. And so Peter Higgs, who, it should be mentioned, passed away earlier this year, and who was indeed a very lucky man to have this idea in his 30s and live to see it confirmed in his 80s. The idea of the Higgs field was really the important part. And Higgs wasn't the only one. It's important to recognize the other gentlemen who were involved in, who made parallel observations of this, the parallel theoretical observations. Yeah. And so Robert Brout and François Englert wrote a paper which was published simultaneously with Higgs' first paper, Englert survived long enough to see the discovery and be co-awarded the Nobel Prize. Brout, unfortunately, had passed away. And there were 3 other gentlemen who worked here in the United States, Tom Kibble, Jerry Guralnick, and Richard Hagen. And they wrote a paper a little bit later. And because it's a little bit later, and perhaps because their statement about the Higgs boson per se wasn't actually correct, there was a tendency, especially in Europe in recent years, to downweigh their contribution. And so but they certainly deserve a footnote, and maybe a little more than that, because they did have the same basic idea. And another person who deserves a footnote is a condensed matter physicist by the name of Phil Anderson, who, again, guessed, without being able to show, that something like the Higgs field might exist in nature, might do something that I'll explain in a moment. But the reason Higgs, I think, became somewhat better known is that it's an accident of history in terms of other physicists who followed along behind him. But one thing that Higgs did, which the others didn't do, was he pointed out that, well, this field, like any field, would have wavicles, and that wavicle might be observable. And that wavicle is what we now call the Higgs boson, even though it's a wavicle of the Higgs field, where the Higgs field was pointed out by 6 different people. Mm-hmm. So it's a strange thing to have a particle and a field named after a person. This is not usually the way we do things. It's a funny accident of our history as a field. People have tried to rename it. I think Higgs himself was kind of embarrassed about it. I mean, it was, so sometimes people just call it the H field. I will not be able to do that. We talk about the Higgs field so much that I'm just going to call it the Higgs field in this conversation. But I think it's worth noting that, the history is more, idolizing Higgs is a little strong. But I mean, he was an important scientist, but he wasn't alone. Now, then there's the word God particle, which is particularly distasteful to me. I think it's an insult. So the second word insults religion, and the third word insults particle physics. and it's an impressive marketing ploy. And it was invented as a marketing ploy to sell books. And having just, started selling books, I understand the thinking. But and it worked. People know the God particle better than they know anything about the physics. But what's unfortunate from my perspective is not only that obviously, the Higgs boson has nothing to do with anything divine per se. What Higgs and his friends did was important not because of the particle. The particle has no role in nature. There are no Higgs particles in this room. There are no Higgs particles wandering the universe. They're very rarely created. And in fact, that's why we had to build these expensive machines to go look for them. So, whereas the Higgs field, that field is present everywhere in this room, throughout our bodies, throughout the Earth, throughout the entire universe, and it's doing something. In some sense, it is switched on. It has a value, as physicists would say, that's not zero. And it's been that way for billions of years. And the universe would be a completely different place if it weren't there and if it weren't doing what it does. And we wouldn't exist in particular. Atoms would not exist. There would be no humans. There'd be no planet. So the Higgs field is absolutely critical to life. It's one of the, you can certainly put it on the top 10 ingredients list for the universe to be as it is. And that's what Higgs and Brout and Englert and Kibble, Hagen, and Guralnick should be famous for, rather than the God particle thingy. The particle was only important as a means to an end. Physicists knew that in order to prove that Higgs and his colleagues were correct about the field, they would have to find its wavicles. There would be no other way. In some sense, the Higgs field in our ordinary lives does only one thing, and that is it assures that the electron and certain other elementary particles have a non-zero and constant rest mass. That's all it does. And since that's all it does, it's very hard to tell that it's doing it. There's no clues other than the masses themselves. And you could dispute, well, maybe the masses come from something else. How would you check? And the way you check is you whack the field and make it ripple. That's
That's how you know there's sound in the room. One of the ways to know there's air in the room is that there's sound. One of the ways to know that there's an ocean is to look at its waves. One of the simplest ways to prove that a field exists is to find its wavicles. That's what the Higgs bosons are. And so finding examples of Higgs bosons, making Higgs bosons at a collider, you can show that you're making them, proves that the Higgs field exists. And that is really important. So the discovery of the particle per se, just another particle. But it's a particle of something very special. And that's the Higgs field. That's the context.
That's the context. There's a common misconception about the Higgs field. And the picture that's painted is this sea of molasses. And everything just passes through it. And the resistance it faces is what gives it this non-zero constant rest mass. You hate this analogy.
I do. With a passion.
With a passion. So let's debunk this myth. How does the Higgs field give a rest mass to everything?
Well, let's start by talking about what's wrong with the analogy, because I think, I don't know if I would have been this 8th grader, but I am sure there are 8th graders who could point out there's something wrong with the analogy right off the bat. So if the Higgs field were like a soup or like a molasses that slows things down, that impedes motion, and if impeding motion was what gave things their mass, then everything would slow down and stop. I mean, if you fire a bullet through molasses, it'll slow down. And if the vat of molasses is big enough, it'll stop. Now, what's wrong with that? Well, a lot of things are wrong with it. First of all, Newton's first law of motion is that if you take an isolated object and leave it alone, it will continue traveling at whatever speed it's traveling forever. So this would be saying that the Higgs field is in total violation of Newton's first law. That would be somewhat disappointing for all of those poor physics students who've learned Newton's laws in their first week of classes, and now they learn that, no, the Higgs field actually makes all those laws wrong. Well, it doesn't. It doesn't do that. Another thing that would be wrong, sort of more direct, is that it would slow the Earth down as it goes around the sun. It would cause friction, cause drag. Well, if you did that, then the Earth would gradually spiral into the sun and we'd be gone. So clearly that hasn't happened in the last few billion years. So something about this story is wrong. And more generally, this story of molasses or soup or snow or a thicket or a crowd of people, there's all sorts of analogies that are used. All of them imply that the Higgs field is like a substance. And as we talked about earlier, a field is not a thing. It's not a substance. I don't know what it is. I don't know what the Higgs field is, but it is not a substance. It's not a thing. It's a property of something, maybe. And I can talk about what it does, even though I don't know what it is, which we will do in a minute. But it's not a substance, and it doesn't slow things down. It can't do that because it would violate these laws that are very basic to physics. I mean, it would violate Galileo's and Einstein's principle of relativity. It violates Newton's laws of the Newton's first law is practically the only law which has survived from the 17th century and is still true today, as far as we're concerned. I mean, we can't be giving explanations of the Higgs field that violate what are fundamental principles of physics, because then you just make a hash of everything and nobody can understand anything. So that's why I hate it so much. And I have friends who feel very differently, but I've made my case. And part of my case is, yeah, but it's not so hard to explain how it actually works. So why are we giving this cockamamie explanation? And the answer to that is, well, I've only got 30 seconds. And it's true. If you only have 30 seconds, my explanation will not fit in that. So I accept that that's true. And I think it's okay to give the wrong explanation as long as you tell people that it's wrong. But we don't do that. So fine. If somebody wants to say the Higgs is like this substance that fills the universe and slows things down, but don't believe me because that's really not true, I'm fine with that.
Okay.
And one of the other reasons that it's a problem is that if it were really true that the Higgs field were like molasses, then everything would slow down. Everything would have a mass that interacts with this field at all. But there are plenty of things that don't get their mass from the Higgs field that get their mass from somewhere else. For example, everything in this room.
The Higgs field gives mass only to certain elementary particles. It does not give protons and neutrons their masses. So it doesn't give atoms their masses because most of the mass of an atom is in its protons and neutrons, which means everything around us, including you and me, gets its mass from something else, which involves the strong nuclear force. And it's a great story, which I tell in the book, but it's not the story of the Higgs field. So how is the Higgs field being so selective if it fills the room, right? It needs to be more of a story. So the Higgs field is something which is found everywhere in the universe, just like any field, but it has a special role to play.
Mm-hmm.
And that role has to do with how it interacts with the other fields. Just to bring us back to where we started with for fields. Okay, so we talked about air being a substance. It's a medium. It has properties: pressure, wind, density, humidity. Those fields all interact with each other. They all affect each other. And indeed, if you're a weather forecaster, what you have to do is you have to figure out how they interact with each other and try to predict the weather tomorrow based on what it's doing across in the United States today. So the universe has a bunch of fields. They do interact with each other. That's essentially why everything happens in nature. It's all because of the interactions among the fields. And the Higgs field has a special interaction with many of the other fields, which lead to their wavicles having mass. So where does this come about? Well, a little earlier, we were talking about the fact that wavicles have mass because they have internal energy. And the reason they have this energy is because a wavicle is always vibrating. But we didn't talk about the fact that there's a direct relation between what happens if you have, let's say, a stationary electron. It will vibrate at a certain rate. It will have a certain frequency of vibration. The vibrational frequency that it has is directly related to the amount of energy it has, and therefore directly related to the amount of mass that it has. So the rest mass of an electron is related to how fast, how quickly, how often an electron is vibrating, which in turn is telling us something about a property of the electron field. Now, how does that work? Well, if you take a guitar string and you pluck it, it's going to vibrate at a certain frequency. That frequency then will create sound waves at a certain frequency, and those sound waves will interact with your ear and make your eardrum vibrate at that frequency, and your brain will then translate that into a certain sound. So the string has this characteristic frequency, which we call the resonance frequency. And no matter how you pluck the string, you do it with your fingernail, you do it with two fingers, you'll get the same note every time. You get the same musical note because you're getting the same frequency. So this is also true of the fields of nature. Each one has a preferred frequency with which it prefers to vibrate. And that frequency is then related to the mass of the corresponding wavicle. So the up quark has a certain resonant frequency that corresponds to the up quark's mass. And the Higgs field has a certain preferred frequency, and the Higgs boson's mass is related to that. So the question of where the particles get their masses is actually translated in quantum field theory to the question of where did the fields get their frequencies from?
Mm-hmm.
And that's the question for which the Higgs field is the answer. So how can it be that a Higgs field, that any field, can change the frequencies of other fields? Well, there's a way in which the Higgs field sort of acts as an environment for everything else. And let me explain what I mean by that by going back to the analogy of a guitar. You know that if you take a guitar and you tune it up and you make it nice so it sounds great, and then you leave it in the sun, or you just leave it outside where the humidity might change a lot, that temperature and humidity will cause the shape of the guitar to change a little bit, and the guitar will end up out of tune in the sense that the frequencies of the strings will shift. So that's a general statement that, well, the environment in which a musical instrument sits can cause it to sound differently, can cause its frequencies to change. And this is also true for trumpet players or flute players. If they take their instrument when it's cold, its frequencies will be a little different than if it's at room temperature. So that's a general concept. And now when we look at the universe, as particle physicists do, again, it's a world of fields with frequencies, it's not so different from a musical instrument, right? It has certain preferred frequencies at which it will vibrate. Just as when you strum a guitar, you will hear certain notes and not others. Now, the universe is somewhat different from a guitar. I'm not saying it's literally the same, but it has this property that there are special frequencies, and the Higgs field acts like an environment for the other fields, causing their frequencies to change. In somewhat more detail, it's a little bit as though if the Higgs field were not there, the fields would all be kind of floppy, and they wouldn't have preferred frequencies at all. They would tend to vibrate. They would tend to vibrate the way a floppy string does. Just sort of however you want to vibrate it. That's how it will fluctuate. That's how it will wave. But if you can somehow make the string or whatever the fabric is that you want to make ripple, if you make it stiffer in some way, you may be able to get it to vibrate at particular frequencies. And that's essentially what we do with a guitar string by fixing its ends. If the guitar string were taken off the guitar, it doesn't have any special frequency. But you put it on the guitar and you fix its ends, you tighten it up, now it has a special frequency. Well, what the Higgs field does is different from that. It's as though the environment itself could make a guitar, could tune up a guitar. So what the Higgs field is doing is it's stiffening the other fields, making it harder for them to vibrate, and making it so that when they do vibrate, they vibrate at a higher frequency. And the higher frequency then in turn corresponds to a larger mass for the Wavicles when they vibrate. So the electron field, in the absence of the Higgs field, would be not much different from the electric field. It would just have waves in it that just, could be made, but could have arbitrarily low frequencies. When the Higgs field is present, the electron field stiffens up. And now, no matter how if you strike it somehow in a particle physics experiment, it will vibrate, but it won't vibrate below a certain frequency. And that minimum frequency, that resonant frequency that it has come from the Higgs field. The vibrations of the electron field, meanwhile, are electrons. And the frequency with which the electron vibrates, again, determines how much energy it has, and that in turn determines how much mass it has. And so the Higgs field, through that somewhat elaborate set of steps, from the Higgs field to the frequency of the electron field, to the energy of vibration of the electron, to the mass of the electron. That is how the Higgs field does its job. And you notice it has nothing to do with motion.
Yeah.
It's not slowing anything down. It's not acting like, it's not impeding motion or acting like drag. No, it's acting like the environment of a guitar. It's changing the frequencies with which the universe vibrates. That's the real story.
You mentioned that the Higgs field is switched on and it's of a particular value.
Yes.
Why is it switched on in the first place? And then can it be a different value? Can it be higher or lower? Why does it have to be this particular value?
So what we mean by value is maybe worth a moment. So, in this room, for example, the wind is calm. Its value is 0, as a physicist would say. And if we turned on a fan, then the wind would start blowing through the room. It would have a non-zero value, and we would see the effect, right? Our hair would blow around.
Yeah.
The Higgs field, in a somewhat similar way, is switched on throughout the universe. It has a non-zero value everywhere. That value is constant, both in time and in space, and has remained so since very early in the universe. Why? We don't know. We can describe why in the sense that we can write equations that would allow for it to happen. We don't fundamentally know why those are the right equations, other than they agree with experiment. But we don't have some sort of conceptual notion that it had to be that way. And in a similar sense, conceptually, we don't know why the value couldn't have been smaller or larger. We do know why it has a value that is rigid and does not change. We know how to write down equations that explain that. But we don't know why that value couldn't have been 0 or much larger. And that's actually one of the great puzzles that we face as particle physicists, in that we do not have an explanation for why the value is what it is. And it's very important that the value is what it is, because if the value was 0, then the electron wouldn't have a mass. If electrons didn't have mass, they couldn't stick to atoms. Atoms would fall apart. So it's very important that the Higgs field not only exists, but that its value is not 0. On the other hand, if the Higgs field's value were as big as it could be, then the electron would have a huge mass, so would quarks, and therefore protons and neutrons. And so every atom would have a huge mass, big enough that it would, either atoms themselves or anything significantly larger than an atom would form a black hole, which would be bad for you and me. We like the fact that we're not black holes, and we'd like to keep it that way. So it's important that the Higgs field's value is not 0, but it's also important that it's really, really small compared to what it could have been. Mm-hmm. And there is no explanation in particle physics today as to why it is so small. And worse, there's no explanation as to how, in a universe like ours, with the types of particles and fields that it has, why it would turn out that it would have a value which is both non-zero and small, in the following sense. When we write down speculative but more complete theories of the universe, which is something physicists do, just to try to understand, well, given what we know, what types of worlds might we be living in? What could it maybe be this way with these additional particles, or could there be some additional forces that we don't know about? And we explore those things just to get a sense for what the possibilities are. In those explorations, in some cases, you can calculate what the value of the Higgs field is. Okay, and again, those are speculative. None of those is necessarily the real world, but they're just explorations. What we find is that in all of those cases, it's very difficult to arrange that the Higgs field's value would be non-zero and small. It always seems to want to be 0 or very big, or as big as it could be. And if you want to make it smaller, you can do it, but there are always additional particles and fields that become accessible to modern ongoing experiments. So, in other words, if there is an explanation of this type for why the Higgs field's value is small, we would have expected that there would be other particles that have masses that are not so different from the particles that we know today, at least the heaviest ones, that they would be being produced at the Large Hadron Collider today and over the last 10 years, and we should have seen a sign of them by now. So, since the Large Hadron Collider has not seen any particles that are elementary other than the Higgs field, it has found all sorts of interesting particles that are not elementary. But in terms of elementary particles, the only particle it's discovered is the Higgs field. It's the Higgs boson, the ripple of the Higgs field. Then the fact that we haven't found others suggests that there's some way that we're thinking about the universe that isn't quite right. Because again, every time we do try to think about the universe in sort of a more complete way and work out in that speculative world how the Higgs field might work and what its value might be, we don't find easily what we actually observe in experiment. So there's a puzzle here. This is called the hierarchy puzzle or the naturalness puzzle. And there are various people out there who suggest that this is just a metaphysical problem. I don't agree with them. It's really a problem of dimensional analysis. So here's a way to say it. You may know that physicists knew that atoms were determined by quantum physics, the quantum physics that Einstein invented or proposed in 1905, that somehow quantum physics was important in atoms. They knew this in 1911, before Bohr invented his theory of the hydrogen atom, which was the first real model of the atom. And they knew this through an argument of essentially an argument about scales and distances based on fundamental principles. They figured this out using a technique called dimensional analysis. In a similar way, Einstein knew before he ever calculated it, he knew that his theory of gravity had a chance of explaining the deviations of the orbit of Mercury from Newton's prediction. He knew it because of an argument of dimensional analysis before he ever started calculating. And I doubt that if he hadn't had that kind of argument, I suspect he would not have taken on that calculation with as much confidence. When you run dimensional analysis arguments in physics, they almost always work. And when they don't work, there's almost always a reason. And dimensional analysis says that the value of the Higgs field should either be 0 or it should be comparable to the scale of the smallest, should be comparable to the mass of the smallest possible black hole. At least if the world is only the particles we know plus gravity. If you add more fields and particles, you have to run the analysis again. But if the universe really were just the fields and particles that we know plus gravity, then this argument should hold. And it just doesn't experimentally. So then that suggests that, well, okay, your assumption that the world is only the particles and fields we know plus gravity should be wrong. There should be other fields and particles around. And in particular, there should be ones that interact with the Higgs field in order to change its value. But in order for that to be the case, the masses of those particles should be comparable to the ones we know. We should be seeing them at the Large Hadron Collider, and we don't. So that creates a somewhat of a logical paradox. And there's presumably, well, I shouldn't say presumably, there is possibly something very important about the universe that we're missing, which explains why this argument is not working. But we have not found it yet. So that's part of why physicists are still very confident that particle physics is not over. It's not the only reason. There's many puzzles in particle physics that we still do not have answers to. It's clear that particle physics is not at the end of its story. If anything, we have more puzzles now than we did before we found the Higgs field, because we might have found the Higgs field and answers to lots of questions, but just getting the Higgs field and one Higgs boson leaves all the questions open. And so particle physics is a long, long way to go into the future. But at least we have kind of it's as though we have a short story that is now sort of complete with lots of loose ends, which tell us there's lots more chapters to read. But the particles we know and the Higgs field together form a kind of complete package, again, with lots of loose ends, that on the one hand, it's a good thing that we now have a coherent story for the particles and fields that we know. And the bad thing is we have all these loose ends and no clues about them. So it's sort of a strange time, because this wasn't true for the past 150 years. For 150 years, well, maybe 140, we've had an incomplete story of particles. And we've known that it's incomplete. And we've known that there's something right around the corner that will help us answer some of those questions. And today, we have more of a complete short story, but we have no idea which direction to go to answer the many unanswered questions that still remain. So that's the challenge for our time.
Let me probe you on this question of why, not just for the Higgs field, but let's expand it even further. And this might be the last big question that I ask you. We've constantly referenced Einstein. Einstein had another quote where he said, "What really interests me is whether God had any choice in the creation of the universe." We've spoken about the Higgs field and the things we don't know and why it exists, why it's a certain value. Let's expand that further to everything. Wavicles, fields, the universe as we know it. I'm interested in the same question that Einstein's interested in, and I hope you can shed some light into this very simple question. Who created all these particles, wavicles? Who created the universe? Are you leaving the door open for a creator, a god, or maybe even a simulation?
What you call simple questions are questions that are simple to formulate.
Right.
It is not difficult to find questions that are easy to state and extremely difficult to answer. And you have picked several of them, and I'm going to call you out on it for this one. As a scientist, I personally try to be very careful to be clear about what I know and what I don't. The origin of the universe, I have no idea. We have no experimental evidence for its history beyond a certain point. We certainly have no experimental evidence, nor is it even clear how one could ever get experimental evidence for how or why the universe exists. And if it doesn't have if there isn't an experimental way in, then we have moved to a different type of knowledge. And I think it's very important to be clear on where that line exists, because scientific knowledge is specifically something that I can test in experiment. And it is not the same thing as truth, because there can be things that you could test in experiment that could turn out to be false because there are contexts in the universe where those experiments wouldn't hold. And if there is a creator that can come in and change the dials and can meddle in human affairs or move planets around, we would never be able to discover that in scientific experiments, because that's external to our techniques. And so the existence of some kind of external intelligence or will or creator or anything that could either have set up the universe as desired or could manipulate the universe now is inaccessible to the methods of science. And that's fine. Science is a wonderful tool. We should understand what it does and not try to apply it where it doesn't apply. So I'm, as a scientist, do not see the question that you've asked as one that science can answer. And so as a scientist, my reaction is, I don't know, and I don't think I'm ever likely to know, nor do I think if I were told the answer, I would be confident that it was the true answer, because I could never actually check it. So I would either just have to believe what I'd been told or remain skeptical about it. So if someone tomorrow came down and from Jupiter and said, "Hey, we've been figuring this out underneath Jupiter's atmosphere, and we know all the truths, and so here are all the truths, and this is how the universe was created, and yeah, there's this group of people, this oligarchy that made the universe and made these choices because it wanted to make sure that these aliens on a particular planet very far from here would grow up the way they do, and you humans, you're just a footnote, you're not the important thing." How would I check that? So in that sense, it's not a scientific question, and I would never know what to believe. And so if you want to ask me a scientific question, I'm happy to answer it. But if you ask me a question which I view as non-scientific, as I do this one, the only thing I can say is this is something which I don't think humans will ever know with confidence.
What does your heart say? Not as a scientist,
right?
As a human.
What is it? What do I say as a scientist? As just as a human being?
Yeah.
So I've grown personally very accustomed to the idea that there are many things about the universe that I will never know. Some of them simply because I will not live long enough to learn them. Some of them because I don't think science can answer them, and therefore, for the very same reasons we've just been discussing, they will remain forever unknowable. And that makes me a devout agnostic, as I like to say. I have no idea why there is a universe. And I think it's important to remember that a universe without something creating it or someone creating it is as crazy as a universe where there was someone who created it. Because, who created the someone, right? The philosophical questions don't get answered. They just simply proliferate. And there was a point made in something I read, I believe maybe by Stanley Fish, although I'm not sure, which stuck with me, which is, imagine trying to explain baseball to a goose. The brain is just not able to get that. And there is no reason to be confident that the human brain can understand every aspect of the universe. It's amazing how far we have gotten with our limited brains through a collective effort. But there may be many things about the universe that we are unable to understand. Just as a goose is never going to understand either the rules of or the reason for baseball, why it exists and why people play. It's not possible. So we have to understand we're limited, and the universe is much less so, potentially. And so as a human, I accept my limitations.
Okay. I'm going to not hold my breath for this as well. If this question likens me to a goose trying to explain baseball, I'm going to keep trying. Fantastic. Before we start moving into our closing questions, I would love it if you can interpret what masterpieces I've built with the Lego. What do you think this is?
Well, I am a particle physicist. And so I work with gigantic structures, or rather my colleagues do, right? The Large Hadron Collider, which is where the Higgs boson was discovered, is a machine for colliding microscopic, extremely microscopic particles 100,000 times smaller than an atom. It's amazing that this can be done. It's a story of its own. But it requires, in order to see what comes out of a particle physics collision, requires gigantic machines, detectors, which are like gigantic cameras in a way, which are several stories tall. So, to run the Large Hadron Collider requires quite a bit of power. So I see a Large Hadron Collider power plant and perhaps part of a Large Hadron Collider detector. And that seems appropriate for our discussion.
It's exactly what I was building.
Yeah, of course it was.
Awesome. Okay, let's move into some of our rapid fire closing questions.
Sure.
What are some books, movies, role models that have strongly influenced you that you recommend?
Well, I think Sean Carroll, my colleague, writes wonderful books. And he's written some books that are for very much the lay reader who has no background in science, but he's also written a couple recently that are sort of for a person who really wants to learn some of the math, but starting from almost no math background at all. And it's remarkable that he's been able to do this. It's the Greatest Ideas in the Universe series, I believe it's called. The first book is definitely out. The second book is coming, I think. And so for those who want to know more, to go beyond, and so my book has no math in it other than the two simple equations I mentioned, but Sean goes more thoroughly into in a very basic way, but in a way that I think is really understandable. And so I would suggest that for those listeners who want to learn a little bit more, those might be good books. Movies. Well, I have a soft spot for Interstellar, and that's the movie in which there's interstellar travel and travel to a black hole, travel to a planet around a black hole. And I think part of what I really like about it is it takes a gee whiz notion that comes out of Einstein's relativity, general relativity, even more than special, which is that everyone lives their own amount of time. And time ticks at its own rate for each of us. Now, this is true right here on the Earth. It's just the effect is so incredibly tiny that it makes no difference. But if you start traveling at far from the Earth at speeds that approach the speed of light, then relative to Earth, then the time that you experience will be different from the time that is experienced on Earth, which doesn't mean that you'll feel any difference. But when you come back to Earth, you will have lived a different amount of time, generally shorter, than people will have lived here on Earth. And if you go near a black hole, there's a similar effect. Being close to a black hole makes time for you pass in such a way that you, in the same amount of time that a person here might live 30 years, you might only live a day. And there's a poignancy to that if you take it seriously, that people who actually, if it's ever possible to travel in these ways, they really will lose the people they love. That their time will really be disconnected from the time back on Earth, and there's no getting it back. And there's this particular phrase that's used in Interstellar that time, we have to think of time as a resource. The time is something to be preserved, and you have to manage it. That concept really captures, in a way, what makes the world so different, time especially, from the way we think it is. We would never on Earth think of as time as a resource in the way that these characters are forced to do so, simply because they are trying to visit a planet that is close to a black hole. And if they don't get out of there fast, they will lose many, many years of life on Earth. And so I just think that, that's a movie which, and partly because a future Nobel Prize winner was one of the key advisors, that it actually captured something human about the physics. And I think that's unusual. Let's say movies, books, and role models. Oh my. I mean, it's hard to say Einstein is a role model, right? I mean, that's kind of ridiculous. But nevertheless, the guy was right about everything. Again and again. I mean, he was viewed later in his life, meaning after the 20s, when he was in his, by that point, he was getting into his late 40s and 50s. When quantum mechanics came along, the way they interpreted in those days, the Bohr complementarity way of understanding quantum physics, and Einstein just wouldn't accept it. And they viewed him as out of touch, getting old and not really in tune with get with it, Einstein, right? Yeah. But he was the one who really understood what was going on. He was, I think, very much the way we think about notions of entanglement today, the way we think about quantum physics today is much closer to the way he was thinking about it. And indeed, if you go back to 1905, where he didn't say light is made from particles. He said light comes in packets. And that is really the right way to think about photons. They're not particles in the sense of dots. They are, in a sense, little packets of light. So he was right about that. And, even where he was wrong, where he put the cosmological constant into his theory to try to make the universe, a static universe, and then it turned out, it was expanding, and he called it his greatest blunder. Well, yeah, but now we find out there is a small cosmological constant, at least something very close to it, in the universe. And there was something in him, in particular, that refused to be satisfied with the philosophical incoherence of the Copenhagen interpretation, of the way that Bohr and Heisenberg and others around him were willing to think about the problem. And on this, he was absolutely right. And so I think a certain willingness to be a maverick and to stick with what makes philosophical sense rather than be satisfied with a sort of let's say an incoherent philosophy and a willingness to just use calculation as a self-justification. I think there's real merit in that. And even though, there's many things that Einstein did later in life which do not seem to have had a long-term benefit in physics, I think it is important for people to understand that he was very, very careful in his philosophical thinking, in a way that I think many physicists are not, and in a way that I personally try to be. And so I guess he would count as a role model in that sense.
Shout out to Albert Einstein. And I'm not looking forward to the gentle tweets I'm going to get from Niels Bohr fans. If there was a genie here today and you have a magic lamp and you could get the answer to one big question or solve one mystery in the universe, what's that one question you would love to get the answer to?
I think the naturalness problem that I mentioned has become the central problem for me. And I view it, again, not all of my colleagues do, but I view it as central because all of the explanations that have been proposed and that some people seem to be satisfied with do not seem philosophically coherent to me. So maybe that connects with the previous question, which is that I think being philosophically clear about what the naturalness problem consists of, about what the hierarchy puzzle is critically important to understanding whether it is a puzzle or not, and whether or not it has already been addressed. And in my view, it has not been addressed, and it is a real puzzle, and one has to think it through carefully to understand why. And it is a question for which I do not yet see a proposal for a reasonable explanation. And for that reason, and also because I think it may be a key question in going forward. That is the question to which I would like to know the answer. Why is it that the Higgs field's value is not zero, it's not huge, and for some reason it is non-zero but small, a fact that is critical for us to exist? I'd love to know.
If you find out, let me know as well. I want to lead my last two questions with two quotes from your book, Waves in an Impossible Sea. The first quote is, in presenting a contemporary viewpoint common among professional physicists, I've tried to satisfy the desire of many readers, the desire I know is out there, for a straightforward, honest depiction of the cosmos as best we understand it. By shining as clear a light as possible on what we know, I hope I'm also demarcating the darkness, the edges of that yawning abyss of ignorance that draws physicists of the present ever onward, and into which physicists of the future, including perhaps some of you, will carry a lantern. Let's talk about legacy. What would you like your legacy to be? What type of light do you want to shine into the future?
Oh, that's a highfalutin question. I'm not sure I have a highfalutin answer. I mean, I think, as a scientist, I have been a synthetic thinker. There's some people who can think very, very deeply about a problem and are great calculators and can do incredible things that I just can't do. But partly because of my philosophical bent and partly because of my skill in making harder problems simpler, I've been able to see connections between subfields or ideas or concepts that have been that have allowed me to be a successful physicist. As a scientist, I probably won't have much legacy. I mean, most of us don't. Part of legacy is luck. I think, Higgs is really an example of somebody who, he didn't write many papers. He just stumbled into the right problem at the right time. Yeah. And so he has extraordinary legacy. And I think for most of us, leaving aside, the Feynmans and the Einsteins and the Bohrs who were going to be famous no matter what, for most of us, there's a certain amount of luck involved. And you try because you hope you get lucky. And I don't think I got particularly lucky in that regard. And so my scientific legacy is pretty limited. But it was fun doing what I did, and I loved learning about it and being a part of it while it was being learned. And I think my legacy may well be to be one of the explainers, one of the people who makes it easier to understand and takes what seems like somewhat impenetrable to the average person and shows that, no, it's not impenetrable. It is tricky. I mean, the world is weird, and we can't get around that. But it's not inexplicable. It is something that many more people can grasp than have been able to. And I would love to be a part of making that possible.
I think there's a lot of value in being an explainer and being the person who either discovered the planets or wrote that book about the planets that you discovered at the age of 4. I think there's a lot of value in that. And even if that's not the case, for someone who was jokingly called the computer who wore boots in grade 6, you've definitely come a long way from that itself. So you already have a much richer legacy. Final question, second quote from your book. Why did I write this book, and why do I hope you'll read it? There are many answers, some of which I'll come to later, but here is perhaps the most important one. If you, like me, harbor deep and existential questions regarding why we are here and what life is about or ought to be about, and if you stare into the empty eyes of the night wondering what it means to be a human being, then I suspect you might find insight, more than you may imagine, through a better understanding of how the universe functions within us. A personal lesson that I myself have learned, drawing upon my long experience as a physicist, is this. It is only with a clear image of how mind and body intersect with the world that one may hope to find a road to thorough self-knowledge and to a full appreciation of what it means to be alive. So for someone who has clearly traveled down this road, I have to ask you about meaning. What is the meaning of life, Matt Strassler? What does it mean to be alive?
Well, I think you can gather from the discussion we had earlier that in a certain way, I accept my limitations and that I will not know the answer to this question. But it is very easy to be misled about what the meaning of life might be, or maybe what should it be, because it may be, we have to make it for ourselves. But no matter what, no matter how you approach this question, how you think about it, if your whole understanding of what you are and of what the stuff around you is and what the history of the universe is completely wrong, you will certainly not get the right answer. So for me, science and knowledge and understanding, to the degree we can get it, is about pushing away all of the things that cannot possibly be true, because they just violate experiment. Mind and body cannot be entirely separate, because we know from
brain experiments that if you fiddle with the brain, you change mind. You change the way mind works. So that's an example of something. It cannot be that these are two completely separate things. And there's all sorts of aspects about the universe at the physical level, which, I think are important to understand. The fact that we are not, in some sense, when one looks at this, little Lego piece, and it looks like, it's just sitting there in the void. It's by itself, but it's not. It's made of the wavicles of fields, and the fields are everywhere. So the wavicles in this object and the wavicles in my hand are connected to each other by the fields of the universe. So there's no sense in which I exist in the universe. I'm part of the universe. I'm the universe doing something. That's what I am. And you can't really understand yourself if you don't know that. So that seems to me something fundamental about the universe and how it works and how we fit into it that most people ought to know before they start trying to figure things out for themselves, which in the end, we all have to do. If you have a foundation which is wrong to start with, you're never going to build something that will work. So getting a good foundation from scientific knowledge, I think, is very important in any voyage of self-understanding.
Well, you seem to have a good foundation. So what's the next step about the meaning? I'm not going to let you go easy.
Well, if I knew the answer to that, I would perhaps be a great philosopher, or I might be a better physicist. I mean, often when you're faced with a really difficult question, which again, simple to state, really difficult to deal with, the problem is you don't really know what the question is. And sometimes knowing the right question gives you the answer or leads you to the answer quickly. And for me, I've always been satisfied with meaning is something that I make for myself, that it's not something that comes from outside, or comes from my relationship with other people. And that's where I find meaning. I find meaning in human relationships. I find meaning in the people I know. I find meaning in the joys of discovery, which I share with other people. I mean, if I had to do science by myself and it wasn't part of a community, I don't think I would enjoy it anywhere near as much as I do. So, meaning for me is about finding a way to do good in the world, trying to find a way to contribute to the human world that we live in. And for me, writing a book about how the universe works is part of that, right? It gives meaning to my life that I spent all these years fascinated by the stars and by the various behaviors of materials around me. And I came to the point that I wanted to, and I did come to the point that I understood a lot of it. And now to be able to make it possible for more people in our society to learn more about it, that gives my life some meaning. It's been a good 10 years of work, and it seems worthwhile.
I agree. I think it's a great meaning to have. Professor, if people want to find you, find your work, find your blog, get your book, where can they go? How can they find you?
Well, I've had a website which has a blog on it, among other things, for about 12 years now. It's called, the address is profmattstrassler.com. It has not only a blog of individual articles that are of individual posts, as most blogs do, but also has many reference articles that are on the website. And it has a whole section about the book, which includes not only information about the book and where to get it, but also supplementary materials that many readers may find useful. Including, it's still being built out, but eventually there'll be many animations of the figures and much more detail about some of the trickier subjects that I didn't have time to cover in the book entirely. So I hope many people will find that website useful.
The website is the place. Professor, thank you so much. It was truly a privilege.
Thank you.